Hello, everyone. So welcome to another panel. This one is going to be about ZKVM design and proof system trade-offs. I'm George. I work on the EF. So working at the EF and kind of seeing the ecosystem of ZKVMs out there, I constantly get questions about proof systems and how they should work and how we should think about security and stuff. So this panel is coming from this angle, and we have people here from major ZKVM projects that will help me explore this. So let's start with introductions from you guys.
So hi, I'm Maya Dotan. I'm from StarkWare. I'm PM for anything proving and privacy related. My background is computer science. So super excited.
Hi, I'm Alexandre, working at Linea. Super excited to be here. I lead the prover team, and we especially focus on developing the proof system and the backend component running the prover. So there is theory and implementation.
Hey, I'm Porter from Matter Labs and ZKsync, and I like math. I was on the security team for cryptography, and they've moved me to DevRel so they can come to more conferences and talk to you all. And so, yeah, happy to be here.
Hello, I'm Stefan from the ZKM. Yeah, so before I joined ZKM 2 years ago, I'm building a privacy preserving projects Eigen network that's also use the ZKP to protect the privacy of some computation. And so that means most of my background are from the engineer, and I also have some years have a lot of experience on building the proof system, especially Stark. Based proof system, yeah.
All right, thank you, everyone. So, okay, so my plan is to sort of start with talking about proof systems, which I kind of consider like the foundations of the ZKVM systems, and then maybe move to more ecosystem topics. So let's start with one topic, which I think maybe let's start with you, Alexandre. I feel like there is you have a distinctive role here because you guys have the only proof system that is using lattices instead of hash-based Starks. And you hear lots of times that maybe lattices are better because of the algebraic structure, but they don't have such good security because the assumptions are more complicated than hashes. I hear this a lot, but these days with all these conjectures and stuff, I don't know if this argument stands so much. So I don't know. Let's talk a bit about how we see lattices versus Starks.
So for lattices, one important thing to know is that there are many different assumptions. So the one we use is ring SIS. And there are different ways you can build proof system using lattices. So if, taking aside what we're doing concretely, one way of doing it is what basically comes from latticefold and other proof system, a long range of work before latticefold is how to basically look at SIS commitments, and try to make them homomorphic and still have security. So it's kind of work with some caveat, and latticefold is a big jump in the sense that now we can have actual proofs of knowledge, and before it was not really possible. The underlying assumption in this case is SIS. SIS is my commitment binding. And there is another common assumption, which is learning with error, which is how you get privacy. We only focus on the binding part because that's how you get snark, and privacy is just something more to get actually zero knowledge. And so we found it, we like it, we found the work really exciting. One caveat there is, so a lattice commitment is extremely fast, faster than as fast as Black 2. That's what we got from our latest benchmark. But that's if you do not have norm bound laws. Because in order to commit to something with SIS, you need to take a vector of field element, break it down in smaller limbs, and then it's all linear algebra. It's extremely fast. You do a sequence of very small FFTs, and you have your commitments. So that's very fast. And the speed of it depends on how big you can afford your limbs to be. So in our case, we target 16 limbs. But for those type of pseudo-homomorphic opening protocols, you need to have like 1 bit. So the speed is like 16 times slower. So what we do is that basically just use sys as a hash function. It's been known since 1996. It's tremendously cryptanalyzed. It's much more secure than Poseidon 2, because we really know the security of it, and there is no any improvement. It's been standardized. Like, we have the tools to analyze it. There are also more fancy assumptions, but those have been kind of broken. So it's still an open question whether we can have it. So it was extremely long.
So I'm curious to hear from like projects that currently use hash-based schemes, if they have considered switching, or like how do they see their long-term going?
So we haven't considered switching to lattices quite yet. We see very good results with the Circle Starks at the moment, which were a big leap forward for us from Starks. Also, like a lot of the problems that it's been known for a while that you can have efficient Stark protocols over that you could potentially have very efficient protocols over small fields. And the problem was at the time to find a field that is small but also has a large multiplicative subgroup. And so Circle Starks is kind of a really beautiful solution to that problem, I think. We're not married to it in the sense that if we find out that lattices beats it by a lot, then we're not against switching, but we see very nice benchmarks and results with 2 now. And even though 2 is really not optimal at the moment because it works so Cairo, we have at StarkWare we have Cairo, the Cairo VM, Cairo machine code, and then x86. So Cairo itself was built to work with our previous stone prover, which operates over a large field. So when moving to the smaller field, we had to make StarkNet work. We had to actually write errors that kind of translate Cairo over the big field to work over the small field. So you have like a simulation overhead. Even with that, we see that 2 outperforms with Cairo code, both RISC-0, SP1, and mostly Jolt. So kind of seems and that's even without having written Cairo that is dedicated to the small field.
At ZKsync, we have a new proof system that I'll talk more about later today called Airbender, and it's like fully Stark-based Fry hash function. But we have actually been talking to Linea as experts in the room on lattice-based hash functions, and we have strong hopes that will be able to speed up some of our the hash function components of the Stark proofs. And so, yeah, we'll see if the research goes. We have some security concerns just for the way we're trying to use them. But if it works out, yeah, we think that lattice-based hashes could be the future.
In our ZKMIPS, we use the Planck 3. So basically, for myself, actually, I don't have much knowledge about the lattice PCS or lattice related NAC, but I believe that we in the Planck 3 right now we have about 100 secure bits, and we also as he said, we also consider the different the proof the security conjunction across different components, especially like we have the proof, we have the stack for the VM, and we also have the proof recursion for the to aggregate the proof, and we also have some of the the final stack to snack wrapper. So for all those components, we all need to consider the security bits.
Right. Okay. So touching on that a bit on the conjectures front, I think I find this quite interesting. Again, like coming from the EF perspective, like kind of seeing how. How the conjectures were introduced into the Stark field, like then StarkWare with the Stark paper introduced the toy problem protocol, like kind of pushing conjectures even a bit further. Like, I'm just curious, like how maybe Maya, you can talk about this, like how do you see this going? Like, are you concerned about the conjectures? Are you concerned about the toy problem assumption? Do you guys actively work to reduce it? Do we think we're going to push it even further? Like how do you think this is going?
So I can't say that this is the main focus of what we're doing right now, but yeah, we're working under the current assumptions. We're not trying to push it further, but yeah, of course, if there is any reason, like, of course, less assumptions, weaker assumptions, always better. So always have our eyes open, but yeah.
The good news about for Ethproofs is that, like, if it turns out that last, like, going outside the unique decoding radius bound assumption is wrong, then you can just do more Fry challenges. And so, like, pretty much all of us could change our code tomorrow and, like, be all right.
Right. Okay. Again, keeping it on the proof systems front, I think another interesting thing is that like StarkWare definitely has its own proof system. You guys definitely have your own unique proof system. ZKsync also has a new proof system. Like, but I see like the rest of the industry kind of gravitating towards kind of like a common Plonky 3, Plonky 2, like gravitational field. I'm wondering like how Stephen, I don't know if you want to say something, like how do you balance between research and engineering, and like, maybe, people are okay with sticking to Plonky 3 and optimizing the engineering versus making new things, like how, since you guys took this choice, how do you motivate it?
Yeah, that's a very good question, because we in our ZKM 0.3 we are using the Planck 2. Yeah, so it's 2 years ago or 3 years ago when we wrote the first paper, we we involved in the Planck 2, and then after we released the 0.3, we we need to say the benchmark from the Planck 2. Yeah, so basically the proving perform efficiency is about maybe 10,000 hertz per second, and it's got logs based, and basically it's very, very slow 2 years ago already. And then, but the one point is the proof recursion in the Planck 2 is very, very fast, because it's customer sockets for the StarkWare file. And then we basically do a lot of research about if we need to upgrade to the Planck 3, or just we replace the hash function inside the Planck 2. Basically, we need to rewrite everything. The air builder, the hash function, and the base field, yeah, everything almost. So finally, we decided to migrate to Planck 3 finally, and then it turns out that we have about 20 times speed up for the VMs proving. So yeah.
Yeah, I'll say there's already a lot of ZKVMs. There's a lot of Stark-proof-based projects, and there's a lot of RISC-V projects. And so why did we still make ZKsync Airbender ourselves? I think probably the biggest reason is just a very, very large dose of paranoia of depending on anyone else's code. And we, just wanted to have something that kind of we control in our project. But as like all of these ZKVMs get really, really good performance, we're like evaluating for the future, like whether we would do another proof system after this.
So I think, first of all, that I like the diversity and decentralization of kind of technology aspect of having many proof systems. But I also think it's, we don't consider ourselves like purists of our proof system. So we've considered like, for instance, 2 accelerates like by design in proving. And verification speed is not its strongest point. So when we consider how to optimize for a verifier, for instance, we do consider writing a dedicated like Plonky 3 circuit for it. We probably won't have to, at least at first, but like there is kind of a good way to mix things up sometimes to get better performance. So we like the general purpose, like Cairo code that you can write and you can prove anything, and it's compatible with our blockchain. But then when you need really fast recursive verification, we don't mind shifting away from that.
So on our side, so our proof system is different, but it's not that different in the sense that purely from a security standpoint, it's using error correcting codes and hash functions. And lattices, it's using lattices just a way to instantiate the hash function that is very convenient to us. So what we get is like very good recursion time and very fast prover time. And verification is still like the weakest point so far. The way we obtain short proofs is different than Fry in the sense that we recurse the proof over itself over and over and over. And like each step reduces the size of the proof by a square root. And at some point we get converged to some constant. So we don't need many iterations, but the constant is still too big. For us, optimizing it is a matter of optimizing the proof system. But from my standpoint, it's not really deviating from the Stark idea. It's just that we are optimizing a few stuff here and there to make things go faster afterward.
But I mean, you definitely have different tooling than the Plonky 2, Plonky 3 crowd, right? Like, so do you see more projects going towards your direction? Have you talked to, like, I don't know, other people that want to adopt your tool chain? Have you?
So right now our tool chain is pretty hard to use in the sense that it's embedded in a monorepo, and for Code it's not optimal. We are not really trying to seek adoption currently because we are developing solely for the Linea network. So every time we have a problem in prod, like something we could optimize, we just do it. But we're not thinking too much for now at spreading the proof system. Also, it's in Go, and most crypto projects are in Rust. So Go is still a popular language. So I guess that at some point people may want to may be interested in using our tool set to build their proof system. But yeah, the good point is that it's very generic, so you can pretty much implement anything you like with it.
Right. Okay. So kind of going a bit further from the proof systems into more like the ecosystem side, like probably you guys have seen like people from the EF talking about, like switching the EVM to RISC-V, or maybe changing whatever hash function we use for the state to Poseidon. Like, do you guys have thoughts on what we should not do as the EF? Like maybe things that you find as bad for the ecosystem?
So we've actually thought a lot about the EVM to RISC-V and things. So as we're not RISC-V experts at StarkWare, but we are experts at proving systems. So there is a lot to be lost when you use RISC-V, both in compilation and so there's a lot of overhead when using RISC-V versus having a dedicated ZKVM and having the entire chain compatible. So we have Cairo, then we have Sierra, we compiled directly to x86, and ARM now also. But yeah, so there's always it's never going to be as fast as if you really want to optimize for extremely fast proving, definitely not ease of development. Like for the end developer, it will be much harder to onboard to a language that's dedicated to ZK. But yeah, but in terms of if you really want your L1 to be provable in real time and scalable, then you might want to pay the price of being the tooling not being perfect, and then deal with that somewhere down the road, write custom errors to deal with that, but not sacrifice the speed.
Yeah, I'll second that. Every team I talk to who's doing a custom ISA has 5 to 10x better performance. And so my advice to the EF would just be yeah, RISC-V has a bunch of teams building this, but we're building for reasons such as just easier developer, bigger developer ecosystem. And we understand there's a performance hit. And if you want to make the decision in that trade-off zone, you're welcome to, but understand that there is a trade-off there.
You mean a trade-off between developer UX and prover performance, right? Yeah. And what do you think? Which side do you think we should take? I think
Okay, so ZKsync has been on what I would call the wrong side of this for a while, which was we have Era VM, which is not quite the same as EVM, and this has been a huge pain point for all of our developers for a long time. I think a month or two ago, we finally added EVM equivalents, which has been a blessing. All of the developer tools start working again, and it's just way better. And so that's part of the reason for going for RISC-V this time is we just want all the developer experience to be really good. And I believe that ZK engineers will just do the hard work to make it ZK so good that it doesn't matter that we're using something slightly not optimal.
Yeah, I was confused because you said I second that, but I felt like Maya's point was that, prover speed is king, and maybe it's worth thinking about the developer experience.
I think I'm not saying one way is definitely the right way to go, because you can build the most optimal thing and nobody would be able to use it, and then you'll just be building alone in the dark. So, but you have to understand there's a trade-off there. So maybe the gap would be not as important if this technology advances enough, but you're always losing something. Yeah.
Steven, you want to?
Yeah. So we are MIPS actually. So yes. Yeah. Of course, we need to consider the trade-off between the proving time and the general purpose for the normal program proof generation. And for us, actually, when we say that we are especially for example, when the foundation say they want to shift to the RISC-V, we are very surprised because RISC-V basically is more older than the Ethereum itself, and it's done means it means the RISC-V is not for blockchain at the beginning actually, but EVM or carrier, yeah, it's for the blockchain at the beginning. And so when we talk about the simplicity, yeah, of course, Vitalik say that the RISC-V is very simple. I would say before we
introduce this simplicity, we should think about what is the simplicity, because RISC-V is modular. That means different actually the very basic instruction sets there, but different manufacturer may have their own extensions. So that means maybe the Ethereum Foundation need to maintain their extensions, even for the bits operations. So actually, that's not simplicity, right? So, but from the, of course, I need to say MIPS is more consistent, and its legacy. It's have everything there. It's more like the superset of the RISC-V. So, but I'm not saying it should be the better answer. But a diversity for the instruction sets should be better. So yeah.
So I think there are two things. Like there is whether we want to be laser focused on making proving ZKVM super fast. In that case, I'd say the most efficient thing is to directly arithmetize ZKVM. It's more work, it's more complicated, but I think it's worth it in the end and can save one order of magnitude of performances that cannot be squeezed by any other mean or by improving the VM, like the underlying VM.
What do you mean arithmetize? Did you say arithmetize the VM?
Yeah, so instead of arithmetizing a VM like RISC-V or MIPS or WASM, you directly arithmetize the VM. So you write the circuits. It's more work. It's like everything is precompiled. But at the end, you squeeze all the juice from the arithmetization, and that's the fastest possible way to do it.
I see. You mean not going through the VM layer, just proof system to EVM directly. Okay, I see. All right. Okay. So going back again from like looking at from the ecosystem layer about security, like Porter, you said like you're very paranoid and like you don't want to rely on Plonky 3. I just wonder like how do you guys see security? Like how do you see like I don't know how many bits of security you're using? Like how do you take decisions on that? And being in an industry where performance is like the most important and people want to get faster and faster, how do you think we should like balance between security and performance going forward?
I'll say like you definitely need like the ZK to be like secure in theory, but most of the bugs we've run into are pretty dumb, stupid stuff. And so part of the reason even for making ZKsync Airbender our new proof system is just to try and simplify some of our prover code. And then we'll add all the normal security things like formal verification and stuff. But yeah, I think we're not as worried about like Poseidon getting broken right now, although I'm glad that there are researchers who are working on that. But like they're really simple things that because these systems are like tens of thousands of lines of code, complicated, only like probably this room of people understands. And so yeah, we're trying to get rid of the basic bugs first.
Yeah, so for us we think the 100 secure bits is the bottom line. So actually when we want to maintain this on the secure bits in a conjecture way, that means we have to consider the VM paths, their lookup, the fly, and then maybe the proof recursion. So there are a lot of different components that we need to make sure the secure bits can meet the bottom line. I think for the secure bits, should be like this.
So I just want to say that like your answer of like that there is bugs on very simple things. We don't need to go to the complicated things. It's not like super reassuring in the sense that it's not like for me there is bugs also in the very simple things and in the very complex things. And yeah, it's true that we need to figure out the small things first, but Like it's kind of saying that we are like, in the baby stages of security still.
Yeah, I don't want to be overconfident.
Yeah.
I do think we're in the baby stages still.
So I agree that we are at the baby stage of security. So I'm very impressed at all the work done by formal verification teams about the RISC-V compiler, and we are looking forward to replicate all the success with our stack. I think this is really the biggest bottleneck for security. Another thing is the proof system itself. So there are two things that can be worrying. So we mentioned the conjecture, like the strongness of the security proof, but there is also the Fiat Shamir things. Recently discovered that actually GKR plus Fiat Shamir was not always working. And it comes from the fact that we use the Fiat Shamir heuristic, and the Fiat Shamir heuristic is essentially a non-falsifiable assumption. We just say that if one protocol is secure when it's interactive, it will be secure with a hash function instead. And there is no proof of that. It just like from the beginning, it's yeah, that makes sense thing in a security proof. So there are some frameworks to analyze it, but the funny thing is that there is actually a proof that GKR plus Fiat Shamir would be secure, but yet it's broken. So I think we still have a lot to learn on that front. On the other side, for the rest, I think it's just a matter of figuring out the right parameters, but I think this part of the security of the protocols, the Stark-friendly protocol, have been figured out already.
Yeah, so I agree that setting the parameters is not I think the pressing issue. Like I think also there is pretty much consensus on what they should be, I think, but definitely I think we're relying too much on like audit to the verifier alone, and so we actually write lean code to formally prove all of our errors, which is a ton of work, but yeah, there definitely needs to be a better standard for soundness and security all around proof. This is super complicated code. There is a super small set of people that are actually able to comprehend it. And a lot of them are malicious in the sense that they would take advantage of anything going on. So definitely kind of, I think in the same sense that in the internet, you wouldn't know where you could put your credit card number because so we're kind of at that stage with proof systems, as I see it.
Right. Okay, I think we are wrapping up this panel. So thanks a lot, guys. Yeah, thanks a lot.